One thing that can be difficult at first if you're encountering how Haskell is doing I/O and side-effecting programming is that you feel that I/O infects everything, right? So because in principle you cannot escape from I/O except temporarily, right? As we discussed, the main sequencing operator in the context of I/O is bind, and the bind operator has the type IOA to A to IOB to IOB. And that means that you can temporarily get access to the A that is resulting from an IO action, but the whole thing will ultimately be an IO action again. And that is deliberate, that is on purpose, that is the whole point, because if something depends on side effects in the first place, right, you cannot suddenly pretend that it does no longer, right? If any ingredient of your whole computation is somehow depending on performing side effects, then the overall computation can no longer be a completely deterministic thing. The overall computation will still depend on I/O. So as soon as something depends on I/O, the whole thing will depend on I/O. And so if you're not structuring your program correctly, you will suddenly end up having I/O types everywhere. But in practice, this is not really the case, because you can structure your programs in such a way that this does not happen. And that is something that you have to learn, right? To separate out the core logic of your programs from the things that actually perform I/O. And that is basically just a way of thinking, and I want to demonstrate this in this video by means of a particular example. And the example I've chosen is that essentially of an expert system. What is an expert system? An expert system is some sort of automated interaction system that interacts with a user and typically asks the user questions in order to provide some answers that the user might have. Expert systems are, for example, used in medical applications. So if someone has certain symptoms and they don't want to immediately go visit a physician, they can interact with an expert system and they're being asked a number of questions, and then the expert system can tell them the likely, I mean, not a real diagnosis, but sort of this is likely relatively harmless, or this could be worse and you should really go see someone, right? So direct someone into the right categories. Another place where expert systems are often used these days are in phone systems for companies. So unfortunately, if you phone a company, you rarely get to speak to a real person immediately. Instead, you're being asked certain questions about what you actually want, whether you have a question about the contract, or whether you have a question about the latest offerings and special deals, or whether you have some complaint to make, and so on and so forth. And you make certain selections, you're getting further follow-up questions, and at the end you're either directly getting sort of some piece of information that you might have wanted, like your order status read out to you through automatic lookup, or you might actually get up and get to speak to a real person, but possibly then already someone from the right department, depending on the answers that you have been giving. And such an expert system, at first glance, it feels like it is really, really deeply interactive, and therefore almost every aspect of it somehow involves I/O. I mean, the whole point is you ask a question to the user, so that sounds at the very least like something like put string line that we've seen before, but it could be asking a question via a graphical user interface instead, or asking a question via audio instead, but all these would also be involving I/O, obviously. And then you have to interpret the answer somehow, and that also sounds like the answer comes in via side effects as well. And if you naively set out to implement something like that, you might very well end up with something where I/O is everywhere. But I encourage you to take a viewpoint where you always try to see computations and processes and things that are happening in a system as data. That is really the right approach to take. Look at the structure, look at what depends on what, look at what kind of different shapes certain things have, and try to give them a representation as Haskell data types. And if we look at it at its core, an interaction is about asking a question. What is a question? A question is a piece of text, perhaps, as an approximation. And then, depending on the question, there are answers, and depending on the answers, you ask multiple questions. So the answers are probably, depending on what kind of, how general you want to be, are of a like numerical nature, that you have like to make a select an option out of many different options. So you essentially give a number corresponding to your answer. Or if you want to be slightly simpler, and that's what I'm going to pursue here, we're just going to assume that answers are just yes and no in this case. So you're only asking yes or no questions. And then, but then, if you look at a particular question, there are just two possible answers, yes or no, and depending on these, you have different outcomes. And these outcomes can be represented as a continuation of the interaction, and that leads to a tree structure, ultimately to a binary tree structure. And we can write down that binary tree structure as a data type. And let's do that. So we can say an interaction is either a question, and a question is a string. And now we associate with a question also the possible continuations of the interactions. And because we said in our case, we want to say there is only two possible answers to every question, right? We have two possible continuations. So we have an interaction. Now that is supposed to be the interaction if the answer is yes. And we have another interaction, and that is supposed to be the rest of the interaction if the answer is no. Right? And at this point, we can represent infinite series of questions that are being asked. But if we ever want to stop, we also need a different constructor for our interaction type that allows us to stop. And let's just say we can also stop with a final result. So basically the expert system can say, I'm done asking you questions, here is my final verdict. And we're using another string to represent the result. And this is a Haskell data type that's very similar to the binary tree data types that we've already seen. In this case, we have a binary tree. We have two sub-interactions in our nodes, and we have our leaves that are results, and both the nodes and the leaves contain certain extra information in the form of a string. Right? We could easily change this type around if we really wanted to like cover different kinds of questions. Right? We might want to put a list of interactions here if we had multiple options rather than just two interactions. Like if we wanted to allow multiple choice questions where we can select from a given number of options, right? We might want to give the different options specific names so that we can list them as well. Then we would put a list of pairs of strings and interactions where the strings are sort of the tagline for that particular answer. These are different variants, but for the time being, let's keep it simple like this, and we just have yes and no, and then the type looks like this. We probably want to derive a show instance for this. And in order to try something out, it will be useful to have an example. So I've prepared one. So let's go down here and uncomment this. So this is actually an example value of the interaction type, the type checks. And it's a little interaction that helps you pick a new programming language to learn. And as we are all already learning Haskell, Haskell is kind of excluded here, right? So we have a little bit of a choice, like, do you want to learn something which also has static types? And then this whole part here is if you answer yes, and this whole part here is if you answer no. And so, for example, if we answer no, then a follow-up question is, do you like parentheses? And then if you say yes to that, then the recommendation is to learn Clojure. If you say no, then the recommendation to that is to learn Erlang. Right? So, and here you have some further questions as well, but you're ultimately going to be given a recommendation. And the point is, this is just data, right? And we have described the nature of an interaction just as data. And we can do all sorts of things now on such a data type of interactions. Of course, one thing that we would really, really like to do in order to check whether we have done a sensible design is to actually run the interaction interactively. Right? To turn it into an interaction that, for example, on the screen asks me these questions and then I can navigate them. Okay, so let's try to do this. So we can do something like run interaction. That takes an interaction tree and interprets it as an IO action of unit result. And how do we do this? Well, by pattern matching, right? This is a new data type, and we don't have many operations on it, but it perfectly makes sense to define something by means of pattern matching on it. So we get two cases here. The question case, where we have the question, and we have the yes subtree, or the yes continuation, and the no continuation. We have to do something there. Or we have the result. Okay. Now the result is actually easier in this case. So if we have a final result, we probably just want to print it on the screen. So we can use putString line for this. Okay. So that prints this, the string that is the result to the screen, and then we're done. Now, in the case of the question, we probably want to do something similar to the ask abstraction that we had before, only that we want to use some kind of yes-no question. So we need perhaps something that makes that a little bit easier to say yes or no to a particular question. So let's perhaps write a little abstraction ask yes no for ourselves that handles just this particular case. So we get a question to ask and we want an IO bool result. We have been writing something that checks whether a line that we input is empty or not, but that's a little bit strange as a yes no. So let's assume we actually want to somehow use the keys Y for yes and N for no. So there are multiple degrees of sophistication that are possible here. So we get our question, and then I'm going to use do notation. I'm going to ask the question first, so do something like put string line q. And then perhaps I'm going to actually indicate, in addition to the question, that I'm expecting some sort of yes or no answer. So just as a little hint, like that I want the user to type one of these two keys. Okay. And at this point, we would have to read some input. And now I prefer to just read a single character rather than an entire line. So we can use a different function for this, which is called getCharacter. And I think this function is not. Oh well, actually no, it is available. So it returns a single character and it does not block, but of course it still has the wrong result type because it returns a character. So we have to somehow turn this character into a Boolean. So we can read this, and then we can check if C is Y, for example, then we want to return true. So that we want to interpret that as a yes. Else, if C is equal to N, then we want to return false. And if it's neither yes or no, I mean, of course, we could like allow the uppercase letters as well, or we could use a default. But we'll just try to read the character, or we will just try to repeat asking the same question. So we're just going to call ask yes no again. So this is our little helper function. And then if we have this, then we can complete our run interaction with ask yes no of the question, and then we get a bool as a result. And then depending on the outcome of this Boolean, we can call recursively, and this is part of the standard design pattern on the interaction type, right? We have two subtrees, and we want to probably call the function recursively, and indeed, if ask yes no gives us true, then we continue running the interaction in the yes subtree, and otherwise we're continuing to run the interaction in the no subtree. All right. So if we try this, right, I should reload and then call run interaction on our example interaction tree. That is exactly the one here with the languages. And now I say, I do like static types, so I type Y. And then it asks me, do you like linear or affine types? And I say, for example, no. And then it asks me, do you like dependent types? And I say, for example, yes. And it says, try Idris. Okay, so this is working. I mean, all that is sort of bad with it is sort of optical impression that we get these characters printed on the next line. It would be slightly easier or slightly nicer if we had printed them on the same line, and then the new question would start in the next line. So, so one way to fix this is to do put string here rather than put string line, and to artificially go to the next line after reading the character by printing an empty string with a following new line after having read the character. Now if I do this, I get something like this, and perhaps we can add an extra space character here. So now it's actually a bit more beautiful. Okay. There is a little bit of a pitfall which I should probably mention here, and that is if you are doing interactions on the screen, you may run into buffering issues. If you're running this from GHCI, I think you're just fine. But if you're compiling this code and you would run it like this, then by default, the standard out handle, that's the stream where output from a program goes to, is line buffered. That means that if we do not print a new line character at the end, it will not actually appear on the screen, and the program will wait for an input without without anything without anything being obviously printed, and that can be very confusing to the user. And so in a situation like this, it is better practice to prevent that by explicitly flushing the buffer. So if you print output to something and you want to make sure that everything is written before you wait for an input, you can explicitly flush the handle, and that is something I should perhaps briefly show. So here we would just add another I/O action that is called hflush stdout. So this is not there at the moment. I have to import a module from the base package that is called system.io that allows us to use this. And now this type checks, and let's briefly look at the types involved. So hflush, I need to reload. hflush takes a so-called handle and then creates an I/O action. And the handle can be a handle for an open file that you've explicitly opened before, or it can be the handle of some sort of global file stream, and that is what we're using in our case. We always have a handle for the standard output available, which is basically the output stream that the process can write to in terms of the console. And that is the handle that we are flushing, and at that point we make sure that the string that we have previously printed, even though it does not contain a new line, is definitely going to be printed to the screen. In GHCI, we won't be really able to observe any difference here. It'll still work just as before, but if we compile this program and run this as an executable, then it does make a difference, and it's good habit if you do not use putStringLine to put an hflush here. Okay, so now we can run our interaction tree interactively. Okay, and we've still been writing quite a bit of code, but this is a general helper function that can be useful for all sorts of things, so you can put it at least in an application-specific library. So this relatively straightforward layer is the part that really describes how we interpret an interaction interactively. But by separating interactions out as data, that is now not the only thing that we can be doing. We can do static analysis on our interaction trees. We can check how many questions are there in our trees. What is the longest sequence of questions we might ask a user before the user gets a final answer, right? These sorts of properties are now very, very easy to answer because there are just tree computations. There are just pure computations on trees. None of this needs any I/O. We can write certain subparts of our interactions in separate places and then compose them together in various ways by just building larger trees out of smaller trees. All these things become possible, and they are not involving any I/O. And perhaps interestingly, we can also write other interpretations. We can write other I/O-based interpretations. So for example, rather than having one that is based on screen I/O or on textual I/O, I could have one that is based on graphical I/O, where I have some sort of window pop up with two buttons, yes or no, and I can click. I could have some sort of web page interaction, right, where this whole thing is happening on a web page rather than on a console screen. Or I could have a simulation, an interaction that is essentially a simulation. And that is something that I want to briefly show. So rather than running this as some form of interaction that is interactive, I can also say, look, if I already have a sequence of answers, in this case a sequence of booleans, a list of booleans, right? I can simulate what would happen if someone is giving this sequence of answers in the current interaction tree context. So I can do something like interaction, and then I have a list of booleans. And then the question is, what is the final result Well, I mean, I'm interested in, first of all, does this sequence of answers get to a result? Does it get to a result node in the tree, or does it end up somewhere else? Right? And then if it ends up with a result node, I want to know what is the result. So I'll choose maybe string here. There are other options, right? We can also say we would want to not return nothing in the case that it ends up at a question, but we would like to list the question as well. So there are certainly different ways of how the simulation function could work. But the one that I'm going to implement now is going to say we succeed if and only if the sequence of answers leads to a result, to a leaf of the interaction tree. And if so, we then return the string stored there. And this is actually rather similar to one of the assignments from earlier in the course. If you remember, there was an exercise where you were given a binary tree and a path data type, and you were supposed to follow the path. And so the types involved were slightly different there, but conceptually we are in exactly the same situation here now, because a list of booleans is essentially a path through the interaction tree, where yes always says we want to go left because we had agreed that our left subtree is the yes tree and the right subtree is the no subtree. So, and whenever we have false, we go right, and the empty list, like the end of the list, is denoting the end of the path. So, so that's basically what we get. So if we are in a question node, and we're never really interested in the question in this particular case, in this simulation environment, we look at the head of our path, and if the head of our path is true, right? Sorry, and I have more answers here. Then I'm going to continue simulate on the left subtree with the rest of the answers. Actually, I don't even need the right subtree. And if I have false, then I'm continue simulating with the no subtree and the rest of the answers. And if I have the empty list, I'm going to fail, but I'm going to do this as a catch-all case. So these are the only two cases that I'm interested in, because it's a list of booleans if the list is non-empty, and these are the only two relevant cases in the situation where the interaction tree is a question. And then the other option is that I have a result, let's say result X or result R. And here it's the opposite situation. Here I want the list of booleans to be empty. And if that is the case, I'm going to succeed with R. And then in any other situation, right, if I either have a question but an empty list, or if I have a result but a non-empty list, I'm going to fail. And that's my simulate function. And now I can also simulate an interaction, and I can say what happens if I say, here I said no and no, and it led me to Erlang, right? So I should be able to simulate this. If I say false, false, it should also get me to Erlang. What else did we do before? Here we said yes, and it got us to Rust. Right. And indeed it does. So it does work nicely. And if we do true, false, we get nothing, because I think if we say true, false, we get a third question in principle. And so true, false, true is going to lead us to Idris, true, false, false is going to lead us to OCaml, and so on and so forth. Right? So this is just an example, but it's actually a rather powerful example. So even though it's like a small thing, this really carries over to larger systems. And it shows that if you take this viewpoint of seeing interactive systems as data, at looking at the shapes of the computation involved, trying to represent things as data, it gives you a lot of power, and you can write things in layers, right? You can write little things around it, and you can write lots of pure code that is also useful. Pure code meaning code that does not involve I/O in this case, such as a simulation function. You can test the entire logic of your interactions by simulating things without needing I/O at all, right? So if you imagine you have a web server, right, and the web server again looks at first as if it's rather fundamentally something that is interactive and even needs networking, but at its core somewhere, really, right, it is probably a function that turn certain kinds of requests into certain kinds of responses. And so you can define a Haskell data type that lists all the different kind of requests as different constructors, including potential parameters for these requests as arguments for these constructors. And the responses probably have structure as well. There are probably different kinds of responses, like successful responses, error responses, responses that carry extra data attached to it. So you can define a Haskell data type with multiple constructors for all the responses as well. And then, as a first approximation, you can define the core logic of your web service as a function that takes a request data type to a response data type, and that doesn't necessarily involve any I/O. Now, in practice, very often you at least need access to a database or something like that as well. But even that does not necessarily mean that you really have to give this request to response function an I/O type immediately. You could, again, you could take a data-oriented viewpoint of a database as well, where you just feed certain extra inputs that have already been determined by the request as extra data into this request response function, so that the core function that actually performs the deep logic does not need to perform actual database requests. That is all doable, right? And then you have a core function again that you can test independently. You can check whether the right kind of responses are given to the right kind of requests without having any I/O whatsoever, without having any networking. And then also, again, you're not tied to one particular I/O-based interpretation. Yes, you can run this as an HTTP service, as a RESTful service or something like that, where you listen on a network and you get JSON bodies as request bodies in, and get JSON request response bodies out or something like that. That is one option. And even there, again, not all of this involves I/O, because you would have a layer where you essentially take yet again a different viewpoint. An incoming request is as a relatively high-level approximation just a string, so you have to write some kind of parser for the request body that turns the string into parses this at JSON and then interprets the JSON as one of these Haskell data types for requests that you've defined. And all this code, from like string to JSON to some representation of a JSON document, and from some representation of a JSON document to your domain-specific Haskell request type, and the other way around as well, from your Haskell response type back to some representation of JSON, back to some representation of a string. This is all pure. None of this involves actual I/O. And only the outermost layer that actually listens on a socket for an incoming HTTP request, something like that, that actually needs some proper side effects, right? And again, you could also say, well, rather than doing this whole thing via HTTP, you do it via a different kind of front end, right? Via a graphical user interface or something like that. So taking this data-oriented view on side-effecting operations is a good way to structure your programs in such a way that you can keep large parts of your code side effect free, usually. And it is really the case that often a sizable part of your code base can essentially just be pure functions, and a relatively small part of your code base is doing I/O. Even though you have, in principle, this thing that certain, like, as soon as you like involve an actual I/O based computation anywhere, the types spread, right? Because you cannot get rid of I/O anymore. But you can decompose things in a different way, as I have hopefully been able to show you in this video.